And thanks for the invitation. Thanks for the organizers for organizing this. It's been a fun meeting so far. So the title of my talk, Universality and Ambiguity and Extremes of Diffusion, and kind of the tagline, the big question in red there is, are extremes of diffusion meaningful? So let me tell you what I mean by that. So, everybody here, I think we all love diffusion. We all love diffusion processes. So why? Why do we care about diffusion? Why is diffusion ubiquitous in nature? Well, you could see this as a consequence of the central limit theorem, right? Central limit theorem says lots and lots of different stochastic processes. Doesn't matter what they're about their microscopic details. Lots and lots of processes. They're Gaussian. They look like diffusion, right? And so in that sense, diffusion is universal. It's ubiquitous in nature, right? That's why even so far we've heard lots of talks talking about diffusion. And I think as the week goes on, we'll continue to hear that, right? And so so another way to put that is the microscopic details of those processes don't matter, at least when you're looking at the process at a certain scale. But we're here in this meeting thinking about extremes, thinking about rare events, and those extreme events, those rare events, those depend on those details, right? Like the bulk of the distribution looks Gaussian. Maybe we don't care about the tails so much typically, but when we're talking about rare events and extremes, we're exactly interested in the tails. So that's where those details really matter. And so with that background, then is the question of the talk: is it meaningful to talk about extremes of diffusion? Right? I mean, because again, lots and lots of processes, they look like diffusion. Those microscopic details don't matter if you're looking at kind of the process at a certain scale. But when thinking about extremes and rare events, those details matter. So is it even meaningful to talk about extremes of diffusion? Of course, that's a big broad question. I'm not going to be able to answer that in any exhaustive way this afternoon. But let me begin to try to address that in the context of extreme first passage times. And I think based on what we've already heard so far, probably don't need too much of an introduction to this topic. But the idea is here you have capital N many stochastic processes. Just call them X1 to Xn. And these are X1 to Xn are, you think about them as the stochastic paths taken by N different stochastic searchers. And then they all have their individual first passage times, call them tau 1 to tau capital N. And as usual, we'll assume that those are II distributed. So you have these independent copies of stochastic processes moving around, and you have when it reaches some target, those are the first passage times, and then the extreme first passage time or the fastest first passage time, I'll call capital T sub capital N. And that's just the minimum of all those individual first passage times. And then, of course, the idea behind these extreme first passage times is that if N is large, if there's many searchers, then that fastest first passage time or that extreme first passage time is much faster than a typical first passage time. Okay, I think we're tracking this, right? Okay. So in this context, so let's now, I'm interested in diffusion. So let's suppose that these stochastic processes, the capital X's, they're diffusion processes. So what's known? So this is, I think, a formula we've already seen today. So this is if I have capital N many diffusion processes X1 to Xn, I look at their mean extreme first passage time or mean fastest first passage time. It goes to 0 like L squared over 4D log N. As N goes to infinity, N is the number of searchers. And then, so there's two parameters in there. There's a capital L and a capital D. What are they? So L is a certain geodesic distance. So L is a shortest path from where the searchers start to the target. And then D is some characteristic diffusion coefficient. And if they're just pure diffusion, then D is just their diffusivity. And so here's a little cartoon in the top right. So this cartoon is for a more general situation. So this formula was first shown in 1983 by a paper by Weiss, Schuler, and Lindenberg. And since then, it's been generalized to a lot of different scenarios. And so this is a rather universal formula. You just have to find what the appropriate L is. So in this picture, I got diffusion in this 2D domain, and there's lots of obstacles. What the L is, the geodesic distance L is the shortest path that goes from the starting location to the target that kind of weaves in and out of the the obstacles. Okay, so this is some of the diffusion, extreme first passage time diffusion theory. I stated this for the mean, but you can obtain the full probability distribution. You can get all the moments. You can extend this to the kth fastest first passage time instead of just the fastest. So this is, let me put some references on the slide. So this bottom left of the slide is this original 1983 paper, and then I put some work that I've done on this. We're extending it to more general geometries and getting the full distribution. And then I tried to find everyone who's at this conference. If you had a paper where you had this formula or something like it in it, I tried to put it on here. If I missed you, I'm sorry. So this is extreme first passage times of diffusion. Okay, and now I'm going to ask, is this theory useless? Okay, so don't be insulted if I put your name up here. I put my own name up there too. I worked on this a lot, and so why would it be useless? Okay, so let me give you a few reasons why we might be skeptical about this theory, about this L squared over 4D log n. So is this theory useless? Okay, so the first one, let me tell you, I went back and forth whether or not I was going to tell the story, but I'm going to tell the story. But I'm not going to tell you who it was. Don't ask me who it was. But so some time ago, I met I won't say who it is, but a very smart physicist, someone that I have looked up to for many years. I've read their papers, learned lots from their papers. This person is way smarter than me, way better scientist than I'll ever be. And I was chatting with him, and he said, "Yeah, I know these extreme first passage time results, and I know some of the stuff that you've done, Sean, and this L squared over 4D log n. It's mathematically very nice. It's rigorous, physically meaningless. It's not relevant to any physical system." And he said, because this is when you're looking at that regime, it's a parameter regime in which the diffusion approximation is not valid. I said, I've been working on these problems for a few years. Really, there's never any parameter regime where it's a good approximation. Never. Okay, so that's sort of one reason that made me feel very small at that point. So that's one reason why I started to get a little bit skeptical of this. Another one is just what I began the talk with, right? This idea that extremes and rare events, those depend on the tails, and that's maybe outside the regime of applicability of the diffusion approximation. To make that a little bit more precise, perhaps this L squared over 4D log n is an artifact of the infinite of what probably people in PDEs would call the infinite speed of propagation, right? You have a solution of the diffusion equation, you have delta function, initial condition. At any strictly positive time, the solution is strictly positive everywhere, right? So we probably remember this from our graduate PDEs course. And so maybe this result, fastest first passage time L squared over 4D log n, you're in that regime where it's just this infinite speed of propagation. And so here I put this formula here. So there's the usual asymptotic, but if I take n large enough, this goes to 0. And so in particular, I can make it arbitrarily small. And if you say, okay, well, if maybe the true process, the true stochastic process is something with a finite speed. So if the searchers are moving with finite speed, call it v, and the target is distance L away, then for sure, nobody's ever going to get there faster than L over v, right? This is minimal search time, minimal travel time. And here's just a graph of, these are a lot of run-in tumble particles or velocity jump processes, and they're all wiggling around. It kind of looks like diffusion, right? You kind of squint your eyes, they look like Brownian motion, and maybe this thick blue one, that's the fastest one. But if they never turned, if they just went in that fixed velocity going up without turning, then they're never going to reach it faster than there, right? So the point is that time is going to get less than that minimal travel time. So that's something seemingly non-physical. So these are already a few reasons why you might be a little bit skeptical of the L squared over 4D log n, this kind of extreme diffusion theory. And then another thing I'll tell you a little bit about in a slide or two is that you can extend this L squared over 4D log n result to anomalous diffusion processes, and you can get some results which are counterintuitive, which also suggest that maybe there's something maybe non-physical going on, maybe not. We'll see. So just say a little bit about anomalous diffusion. So anomalous diffusion is, a broad category of stochastic processes. Generally speaking, though, they have this property of a nonlinear mean squared displacement. So there I have, the way I think about mean squared displacement, I always read it backwards. So the displacement is how far you've moved, and then I square it, and then I take the mean. So the mean squared displacement, if I say that grows according to a power law, then you distinguish it into three cases. So when alpha is 1, the power there, alpha is 1, is just a linear mean squared displacement. That's normal diffusion. And then subdiffusion is where it grows according to a power alpha less than 1, and then super diffusion faster than 1. So this is sort of quick overview of what people generally mean when they talk about anomalous diffusion. Now, anomalous diffusion is a very broad category of processes that that have that emergent behavior. There's various models of it, but let me tell you some fastest first passage time results for some popular models. So this first equation here is for a number of different models of anomalous diffusion, including what's called scaled Brownian motion. This is effectively a time-dependent diffusion coefficient, where the diffusion coefficient either grows or changes according to a power law, or fractional Brownian motion, or what's called Riemann-Liouville fractional Brownian motions. These are just broad categories of Gaussian processes, which can be anomalous diffusive, be anomalous diffusions with according to different powers alpha, and you get a similar L squared or 4D log n. You have this time constant. That's the time constant appearing here in the mean squared displacement. But you get the power 1 over alpha. And another common model of anomalous diffusion, particularly subdiffusion, is what's called a fractional Fokker-Planck equation. And for those such processes, you also get a 1 over log n behavior, but it's a log n to a power that depends on the anomalous diffusion exponent alpha. But the point about what is counterintuitive here is that you just notice, you say, well, if alpha is smaller, then these go to 0 faster. Right? So what that means is that for these extreme statistics, subdiffusion is faster than normal diffusion, right? And if power was an alpha, then if alpha was a half, I got 1 over half. I got then now it goes to 0 like 1 over log n squared, right? It goes 0 faster. And then similarly, for this top equation is valid also for superdiffusion, and so then normal diffusion is then faster than superdiffusion, right? So this is sort of counterintuitive, not what we would expect, right? We think about superdiffusion as being the fastest and subdiffusion being slow, but it turns out in these cases the opposite is true for extreme statistics. So what I'm doing is I'm just trying to building a number of reasons why we might be skeptical of this L squared or 4D log n. Okay, and so so then the question: is this counterintuitive behavior in which subdiffusion is the fastest and superdiffusion is the slowest? Is that somehow an artifact of the infinite speed of propagation? Okay, you guys, people tracking? Okay, so now let's try to there's different ways you could approach this, but let me tell you one way that I've been thinking about it. And this is, okay, well, let's see if we can do some of this analysis on some bounded speed processes. So let's think about what I'll call here some, bounded speed diffusion. And so what I'm talking about here go by a number of different names. I put RTP there for run and tumble particle, run and tumble process, or sometimes called a velocity jump process. I think we'll hear a talk from Maria later this week on velocity jump processes. And so these are processes which move at a fixed velocity for a random amount of time, and then at that random amount of time they switch directions. So in one dimension, this is just you have a fixed speed, and then you just switch directions between going left and right. And so I'll let x sub epsilon be one of these one-dimensional bounded speed diffusions, these run and tumble particles. It has a constant speed, which I'll call v naught over epsilon, and then it'll switch directions at some rate, lambda naught over epsilon squared. And it's well known that in this fast switching limit, the limit that epsilon goes to 0, right? So you're moving faster and faster, but you're switching directions more often. It's well known that this bounded speed diffusion, or this run-and-tunnel particle, or this velocity jump process converges to a Brownian motion, where the diffusion coefficient is just this ratio of the square of the velocity over twice the switching rate. And okay, so that's sort of well known for normal diffusion processes. You can define anomalous diffusion versions of that, and I'm sort of sweeping the details under the rug. You can look at the paper. We could talk about it afterward if you want to. And then these are just some simulation plots of the different versions, right? So on the far left is normal diffusion, just this run-and-tumble particle, right? You have fixed speed and you switch directions, and there's a subdiffusion analog of it and a superdiffusion analog of it. Okay, so these do not have infinite speed of propagation, and let's see if some of these diffusion theory is still useful here. So first off, it's not too hard to see that if I fix all the parameters and I take n to infinity, the number of searches to infinity, then this fastest search time, this first fastest time, is just going to go to the minimal travel time, because what's going to happen is that eventually one of those searchers, if n is large enough, is never going to change directions, and they'll just go straight there, and so they'll have that the time is at fixed velocity, or that the time it takes if you're moving at a fixed velocity. And then I'm not telling you the details, but so that's sort of clear that you're going to go to that minimal time, and turns out you can prove the convergence and distribution, where the correction comes from a Weibel distribution. So that's sort of a theory for the large n limit. But then the other limit is where you're thinking, suppose I take epsilon very small, so they're almost a diffusion process, almost a Brownian continuous diffusion process. And so there you might naively expect, okay, if I'm going to take epsilon very small, so they look like diffusion, I'm going to take n big, but not too big, right? Not too big that you're going to be in the regime of these first two bullet points, but large, but still large. And it turns out in that case, and I'll just illustrate it with some graphs on the next slide. In that case, then the diffusion theory, and including the anomalous diffusion theory, still holds. So that is to say, going back to the question, is this extreme diffusion theory not physical, or just an artifact of the infinite speed of propagation? The answer is no. It still applies here. So if I can have these bounded speed processes in not too large, and the diffusion theory still works. And I'm going to try to illustrate that on the next slide with an extremely complicated graph, which I'll kind of show you one by one. All right. So this is here's a graph. You can just ignore this because I'm just going to add some more stuff. So you can ignore the legend. But these are three different plots for different values of epsilon. So recall, epsilon is the parameter. As epsilon goes to 0, these bounded speed processes look more and more like diffusion. And I'm plotting number of searches on the horizontal axis, and the vertical axis is this mean fastest first fastest time. And so what's shown on these three plots are all identical for these three plots. So the curve is this bounded, or is the diffusion theory. It's the L squared over 4D log n. Actually, to be more correct, it's the L squared over 4D log n plus the two higher order corrections you can get in terms of a Lambert W function. That's what the curve is. And then the circles are simulations of the unbounded speed, the continuous Brownian motion diffusion theory. Okay, and then now what those pluses are simulations of the bounded speed diffusion, the bounded speed diffusion, the run and tumble particle. And what do you see? You see that if n is not too big, it looks like the diffusion theory, especially if epsilon is small, right? So for here, epsilon is very small and they're indistinguishable. And here epsilon is pretty small, and they look pretty close unless n gets too big, and then similar story in the top left. And then you can add on to that some of the bounded speed diffusion theory, which I quickly showed up in this sort of Weibel theory. And for real small epsilon, you can't even see it on these graphs. But for here, epsilon is not too small, and the bounded speed theory then. So the idea is that if n is not too large, then the continuous Brownian motion diffusion theory is valid and is very large than the bounded speed diffusion theory holds. And so that's all normal diffusion. And then if you can now look at the subdiffusion version of it here in blue, the curves have the same meaning, but now for subdiffusion. And the key thing to observe is that even for these bounded speed processes, the continuous Brownian motion unbounded speed theory is still valid for small epsilon. And in particular, the blue is now here for subdiffusion, and the point is that the blue is lower on the graphs than the black. So that means that the subdiffusion is indeed faster than normal diffusion here, even for these bounded speed processes. And then last, the red is for superdiffusion, and the same thing true that the superdiffusion is the slowest. Zach, yeah.
Can you get a formula for N1, or did you already tell us?
You can get it. I didn't tell you what it is, though.
Okay.
Yeah.
And it has to do with epsilon somehow.
Yes, that's right. Yeah. So yes, epsilon gets smaller; those get much larger. Yeah.
Okay.
Yeah. Sorry. No. Yeah. It's in the paper. I didn't put it up.
Okay.
It would be something which I would consider probably as like kind of model dependent. But yeah, you can. Yeah. I forget what it is, but yes. Yeah. Okay. So then I'm running out of time. So let me just wrap up with this slide. So are extreme first pass times of diffusion meaningful? Yes. Okay. So if I put your name, if I put one of your papers up on the slide earlier and I put, is this theory useless? The answer is no. I think it's useful. I'm not insulting you. If I was insulting you, I'd be insulting myself too. So yes, I think that, this extreme diffusion theory, it was developed for Brownian diffusion that has an infinite speed of propagation, but yet it's still it's not an artifact of that. It still holds for these bounded speed processes. It's also turns out to be valid for discrete processes. So you could imagine your microscopic process is not a continuous Brownian motion, but it's a discrete Markov jump process on a discrete state space, and in the appropriate limit. Like in the case where that looks like diffusion, but it's still not in the diffusion limit, this extreme theory still is a valid approximation there, it turns out, and I didn't show you that, but it turns out to be true. So yes, but I still think we should be careful, right? So this is just like this graph showed, is that the continuous unbounded speed extreme diffusion theory is valid in certain regimes, right? And so I think one has to be careful, maybe especially careful when thinking about extreme statistics in rare events, to be sort of aware and checking if we're still in a parameter regime in which, say, the diffusion approximation makes sense and still valid. And so this is a paper. It's on the archive. So more details are there, and I'll be around the rest of the week. So I'd be happy to talk about more about this. But I think maybe I'll just end with this general thought. So here I was, in this talk I was focusing on extreme first passage times, but I think it's generally an interesting and important and hard and question of thinking about extremes of diffusion and when those microscopic details of the process do and do not matter, and sort of just being able to understand that, I think, is a bigger question which could use some more work. Okay, so that's all I'll say. Thanks. Yeah, Jay.
I've always wanted to see the numbers work out for like the physics Langevin equation, where we track the velocity for like a spherical particle and room temperature water. What's the end?
Yeah.
What's the end where things start to diverge?
Yeah, that'd be a fun calculation to do. Yeah, I would think it'd be readily doable.
And it should be like a really large end, because I think that the dissipation times go like insanely short, right?
So you're saying that you would expect in that case the continuous Brownian motion theory to be valid because there really are like diffusion processes. Yeah, I think is right. But yeah, that would be I think a worthwhile calculation.
Ethan, I think Ethan had a question over there. And then just Samantha.
First passage time. So have you looked into, like, if I were to look at the variance for these different processes, maybe like one of them is kind of exploding or
Yeah.
differences there?
I haven't thought a lot about that. Yeah. I think I would expect it's doable. My gut would tell me it wouldn't be that different, but it could be. It could be. There'd be probably some differences. That would be interesting to think about.
I'm wondering if there's some intuition you have for why the diffusion theory holds in this kind of, in my view, like not so extreme environment of small epsilon and small n. Like that's where we're seeing the old extreme
Yeah.
hold. To me, small epsilon, it's like, oh, your max propagation speed is like not that fast, and it's not that big. So that's like not that extreme, but we're seeing this hold. So like, as you say, we need to be careful. And of course, these extreme diffusion theory results hold exactly for large n, but we're like extrapolating to small n. So why are we seeing that agreement?
I don't know. Yeah. Don't ask me such hard questions.
Question here.
Man, you asked me hard questions for years.
Andrew, last
But
one.
it's a good question. Yeah, Don.
So in the bounded speed process, you showed or told that, argued that the minimum time is the ballistic particle that just makes it there, right? But ballistic is very super diffusive. So now I'm extra confused why super diffusion is slow. Is it because you choose the wrong direction most of the time or something?
Okay, no more questions. Yeah, no, I don't have a lot. So why super diffusion is the slowest? I don't really have any good intuition. Let me just say something which is not at all deep and very superficial, but I somehow perhaps is maybe right. It's just that, T to the alpha, if alpha is bigger than 1, T to the alpha is big unless T is small, right? So just I think basically that's what's happening. Does that make sense? But connecting it with the ballistic motion, I don't have a good intuition for that. Yeah.
Okay, let's thank Sean again.